Bismillah ar-Rahman ar-Rahim. This is tutorial number 3, and we have 3 questions in this tutorial. Let us start with question number 1. So it says that for the ramp function shown in this figure, they determine the fundamental frequency in hertz and then find the Fourier series. Okay, so we know that the period is given as 0.5, so 1 over 0.5, and it is in milliseconds, so that will be 2000 kilohertz. Now let us find the Fourier series. So we know that the Fourier series for any signal can be given as the DC component plus summation of A in cosine in omega t plus summation of B in sine in omega t. The DC component will be the area under the curve, so we can take the integration. So this function will be t, it will be 2, if I like to write the equation, so that means the equation will be 2t divided by t. So this one will be the equation for this curve over here. So 1 time is equal to t, vt will be equal to 2. Okay. So now we can take the function and then take the integration for 1 whole period, which is from 0 to 0.5. And then we divide by the period, the result will be 1. Therefore, the DC component will be 1. Now let us look at the AN component. So AN component, we have to take the function, we multiply it by cosine, divide by t, multiply by 2. Now we have 2 variables. We have t variable, cosine in omega t variable. We can take the integration by using integral by part. So integral by part, if you have u dv, the result will be u times v. So we take the integration of v, then subtract the integral of, again, v time derivative of u du. So then we're going to use the integral by part to find the result. So this one will be the result. If we look at the integration over here. Okay, so this is the integration. So we have u that will be the time t, and dv will be cosine in omega t. Okay, so then will be the result will be equal to u, which is t, then time v, which is the integral of dv. So the integral of cosine will be sine in omega t over in omega, then minus again the integral of v, which is again sine in omega t over in w, time derivative of the first, which is dt. The result will be 0 for AN. For BN, the result will be, we can do the same procedure. We're going to have minus 2 over n by, where n will be from 1 onward. Therefore, the function can be written as a DC component plus the coefficient for the sine, wave. Okay. Actually, we can do Fourier. We can do this problem by using MATLAB. So let me show you. Okay, so this is the MATLAB file for the ramp function. If I run the MATLAB file, see the ramp function. This is the ramp function. Now, if I like to see to do the Fourier analysis, so go to Tool, click on that, and then say display, and that will give you the DC component will be 1, second harmonic, third harmonic. Of course, this one, if you like to see the value, if you like to see the bars, this is how the bar will look like. Okay, so that is for the first problem. Now let us go to the second problem in the tutorial. Okay, so in second problem, say that a pulse waveform shown over here, and the peak value harmonic spectrum is shown over there, and those voltage will be applied across the 50 ohm. For part A, determine the root mean square voltage of the signal using harmonic component shown over here. Okay, so now what we have we have DC component, fundamental, third, fifth, and seventh. So to find the root mean square, we need to take each one, but of course those are the weak, so we need to divide by root 2. Okay, so that will give us the root mean square value. Then for part B, determine the power absorbed by 50 ohm resistor considering the DC component in the first 4 non-zero harmonic. Okay, so the power dissipated by the 50 ohm will be V square over R, so 0.5 square over R. Then this value square over R and so on. So that will give us the power dissipated by each fundamental, third, fifth, and so on. Then if we take the summation, the total power dissipated will be 0.7, will be 0.74. Okay, now if we go back to the question number C, it says that determine the root mean square voltage for the pulse waveform. Okay, so we need to determine the root mean square voltage for this one. Of course, we know the equation for the root mean square. So we know that to be root mean square will be given by the square root of 1 over the period, and over here the period will be 1. Okay, so and then we'll take the integration from 0 to 0.5 millisecond. The function will be 1 dt. Okay, so and of course the function will be square. So the integration of dt will be t, and then it will be 0.5 minus 0, that will be 0.5. So square root of 0.5, which will be 0.707. So that will be the root mean square value for the whole waveform. And then we need to determine the what will be the power dissipated. So the power dissipated will be V square divided by 50, that will be 10. Of course, over here we obtain 10, and when we do Fourier, we obtain 9.97. What are the difference between the two? Because in the Fourier we didn't take into consideration all harmonics. We stop at 7th. But if we consider all, of course, we're going to have identical result. And this is the power variation against the frequency. So DC component fundamental. Okay, for the third question, say that derive the Fourier series for this waveform. Well, this waveform look like sinusoidal, but without a negative negative side. So we need to find the DC component. First of all, so we take the 1 over the period, then we take the integration. So we know that the period will be 2 pi integration of the function, which is sine d theta. Take the integration and find the result. For an, we take the function multiplied by cosine, take the integration, and then we're gonna end up with this result as it is shown over here, right? So for the for n, if n is odd, n will be 0. If n is even, n will be that one. And then we can find bn. Again, bn will be also 2 over t, and take the integration from 0 to t. Then we're gonna end up with this result. So bn will be 0 for all harmonics except the fundamental. Fundamental will be a over 2. Then the function can be written as dc component plus the bn part plus the an part for the cosine. So that will be the harmonics. That will be the Fourier analysis or the Fourier series. We can do the same thing in MATLAB. So let us say that if a is replaced by 1, so if we take this kind of signal, okay, and this one will be 1, then the DC component is supposed to be 0.318. Let us do this one also in MATLAB. So this is MATLAB, and let me open the file. Okay, call it tutorial question number 3. Okay, well, how I create that signal, actually I use voltage source, sinusoidal, then I made rectification. So now let me show you how the waveform would look like. So you see that look like sinusoidal but without a negative. Now if I do again, if I do the fast Fourier analysis, and then I try to display the results. So you see that DC component will be 0.32 as we obtain it by using an analytical way. So you see that it gives you the DC and all harmonics over here. And of course it says that the total harmonic distortion will be 43.5%. That's all. Thank you.